So now that we know how to solve a large category of differential equations, specifically constant coefficient linear differential equations, let's look at an application, a long-awaited application. Now, we're going to just look at one application here, but it's a very natural and fundamental application. And just keep in mind that there are actually many large numbers of applications of these kinds of differential equations, and the book talks about some of the others. We are going to focus on the application of a mass on a spring. So here's the picture of what we're talking about. We have a mass attached to a spring, which is itself attached to a firm support up above it, let's say a ceiling joist or something like that. And the idea is that this mass on a spring is going to move. If someone were to take the position and pull it down to here, now the mass is down here, and then let go, well, the mass would, of course, start moving up, and then the spring would push it back down, and then once it goes a certain amount of distance, well, it would at some point start to pull it back the other way. And altogether, reasonable question, what is the motion of this mass? What is the position U? Notice that this is our U axis, indicating the location of the mass. What is the position as a function of time? Okay. So we're going to study this by looking at the various forces that are involved. For one thing, there is the spring force. And this is a standard thing from physics. Students might remember this from high school, but depending on the position, depending on how far the spring has been moved from its natural position, there is a force that the spring exerts. It's proportional to how far the spring has been moved from its natural position. And notice that with this minus sign is indicating that this is an opposing force. So if the mass has been moved in that direction, the force, because of the minus sign, is in the other direction. And of course, that's how springs work. Okay. Friction. There's a potential that there's friction in play here. So, for example, maybe there's air surrounding the mass, and well, as the mass moves through the air, there's a certain amount of drag, friction, sometimes called dampening. Okay, and there may be some sort of external forces. So maybe this mass is made out of some sort of a metal, and there's a electromagnet down here with a dial on it. And somebody is turning the dial back and forth over time, thus applying these external forces. And we're just going to leave this open as with some function of t. And we'll come back and consider different cases of that later. Okay. So altogether then, all of these forces add up in total to this. Don't forget that F is equal to ma. Therefore, all of this is equal to ma. Don't forget also that acceleration is the second derivative of position. So altogether we get this, and that can be rewritten as that. And specifically, note that this is a constant coefficient. Mass is constant. The friction coefficient is constant. The spring coefficient is constant. Constant coefficient, linear. It's got this linear form. Differential equation. Okay. All right, so what we're going to do now for the rest of this section is solve this differential equation in various special cases. We're going to start off with the easiest special case, and that is where there is no friction and also no external forces. So you'll notice here that there's a conspicuous absence of the friction term. Right. Okay. Also, no external forces. Therefore, no h of t over on the right. So our differential equation simply turns into this. And we know how to solve these differential equations. Step 1, write down the characteristic polynomial. There it is. Step 2, find the roots of this characteristic polynomial. No problem. There they are. And this quantity here, square root of k over m, we're going to write that as omega naught square root of k over m. This is referred to as the natural frequency of the system. It depends, of course, on the mass and the strength of the spring in question. The terminology natural frequency is a bit of an abuse. Don't forget, of course, that frequency is actually omega naught over 2 pi. Now, think back to your trigonometry class in high school. But nevertheless, the terminology is pretty standard, and it's just kind of inconvenient to deal with that 2 pi all the time. Okay. So that being said, here's our roots. Our roots are plus or minus I omega naught. These are imaginary. We know how to write down roots that correspond to imaginary, more broadly, of course, complex roots. And here's the fundamental set of solutions right there. Cosine omega naught t, sine omega naught t. So again, think back to trig class from high school and persuade yourself that the actual frequency here isn't actually omega naught. Strictly speaking, the actual frequency is omega naught over 2 pi. Okay. All right, so we have a fundamental set of solutions. The general solution, of course, is just all possible linear combinations of that, and you could declare victory at this point. We do have all of the solutions. Importantly, though, I want to rewrite these solutions. This general solution, turns out there's a very natural alternative way to think about it, and that is that every one of these functions, every linear combination of cosine and sine of the same frequency, mind you, omega naught t, these can always be rewritten as a single sine wave, like this. Note the same frequency. Note here that there is a phase shift, and again, think back to trig class from high school as to how this is interpreted as a phase shift. The fact there is a minus phi here, how that makes a phase shift on this cosine wave. Not immediately obvious that everything of this form can be put into this form, but it's easy to check by simply expanding the angle addition formula for cosine, and thus rewriting this as this. And now notice we're trying to show that everything of this form can take this form. You see that there's a cosine omega naught t, sine of omega naught t in both of these. And so this is accomplished simply by C1 being a cosine phi and C2 being a sine phi. It's a nice little observation there, little slick little bit of trig. It's important for students to be comfortable with this kind of an argument. So specifically then, if you have C1 and C2, and if you want to figure out what A and phi are, notice how exactly do you put one of these into this form. You need to figure out what are A and phi. Then these are the relationships that do it for you. C1 is a cosine phi, C2 is a sine phi. And think back to, again, your high school trig, and recall this triangle, a cosine phi, a sine phi. A is that distance, phi is that angle. That means that C1 is that value, C2 is that value. So if you know C1 and C2, that tells you where this point is, and given where that point is, you can deduce what the angle phi is, and you can deduce that distance A. Now, students should make sure that they're comfortable with doing this sort of thing and determining from these equations what A is and what phi is. Okay. All right, now you'll notice that in this first case that we considered, in addition to there being no external forces, there was no friction. Conspicuous absence of friction term there. So what if we reintroduce friction back into the system? There's the friction term now. Now how does that change things? And by the way, again, this is pretty physical. You can have a mass on a spring. There's the mass. There's the spring. And again, that mass, maybe a cannonball attached to some sort of sufficiently strong spring, well, it's moving through the air, and there's a certain amount of friction resistance there. So it's natural. And we might want to understand that motion. Now, by the way, what we sort of expect to happen in that scenario, if I try to expect what u would look like as a function of t, then it's not going to oscillate forever because there's friction involved. And what we sort of expect is that it would oscillate but slowly deteriorate over time, some form or another, because of the friction. Right? There might be a lot of motion at the beginning, but over time the friction will take over and there just won't be very much motion at the end. So let's see if that bears out. Okay, so, well, characteristic polynomial. Find the roots of the characteristic polynomial. The quadratic equation tells us the roots are these. And a couple of observations I want to make about these roots. For one thing, notice if you plug in f equals 0, this does simplify to the previous formula, what we worked out on the previous page. And students should plug in f equals 0 and confirm that this does give you that familiar result. The second thing I want to observe about this is that the real component of this is always negative. And that's not immediately obvious at a glance, but this is true. So there's two different possibilities that we would have to consider here. One is this value under here, as you might recall, this is referred to as the discriminant. That discriminant might be negative, in which case this is imaginary, and the real part, you can see right there, clearly negative, because, of course, f is positive, m is positive, and therefore that minus sign makes this real component actually negative. On the other hand, this discriminant here might be positive, in which case this square root is real. And then I can't just focus my attention on this and say it's clearly negative. Now, if this is actually a real square root, then I've got to worry about which is bigger, f or the square root of f squared minus 4mk. And conveniently, we can at a glance observe that f squared minus 4mk is clearly less than f squared. And so therefore, this expression here is less than f, and therefore this total, again, because of that minus sign, still negative. Okay. All right, so the real component is always negative. Okay, so now let's consider cases. Again, we have the roots, and let's take these roots and write down solutions per our methods from the previous lectures. And let's see what these solutions look like. Now again, we have to break it down into cases. We'll start with the case of the negative discriminant. So that's under the radical there. Let's suppose that that's negative and see what we get. Of course, that makes this square root imaginary. That makes the roots complex. They're going to look something like this. The a and the b are formulas that you can write down. And now you will notice that I have specifically put the minus sign in there. Right? I've exposed that minus sign because I want to see that minus sign in the solution. That's the minus sign that came from our understanding that the real component is always negative. So in particular here, note that the a value is positive, thus making this real part actually negative. Okay. So that gives us solutions that look like this. Here's that fundamental set of solutions. As per previous lectures, we have an exponential times cosine and an exponential times sine. The general solution, of course, is all linear combinations of those. And noticing that this exponential is a common factor, further noticing that what's left over, C1 cosine, C2 sine, is exactly what we had in our frictionless analysis, we can instantly rewrite that trig as this, exactly like the algebra that we did on the previous page. So altogether then, here's what our solutions look like. And you can see in the form of this expression the decaying oscillation. Here's the oscillation right there. Cosine bt minus phi. That's an oscillation. Up and down, up and down, up and down. And there's a phase shift, and there's a frequency, etc. But you can also see here that this is a decaying oscillation. Because what you might casually refer to as the amplitude here, it's not just some number A, it's that times this decaying exponential, which means that sure, this green term is oscillating, but the amplitude of that oscillation, because of this decaying exponential, is slowly decaying. And so as we sort of anticipated, this actually looks kind of like this. Let's see here, yeah. Kind of like that. This exponential, this decaying exponential is controlling how the amplitude decreases. Okay. Okay, now there is a bit of a concern that we need to address now, though, and that is, don't forget, this was just the first case. This was just the case where the discriminant was negative. We have to consider two other cases. This discriminant does not have to be negative. It's entirely possible that this discriminant might be positive. Maybe f is really large. Maybe m and k are really small. Now, we weren't visualizing things that way in the first place. In the first place, we were imagining a cannonball, thus making m big. Let's see here, I'll say big. A very heavy cannonball attached to some sort of a strong spring here, thus making this value big. Right? And it was moving through air, just this very light, air, just air, which would suggest that this number was small. So the way we phrase this question, the manifestation of the problem that we were visualizing to start off with, suggested that we had a small positive number and then a big negative term over here. So we were thinking in terms of a negative discriminant, but that doesn't mean that it has to be. Again, it does not have to be a cannonball moving through the air. It might be instead a Nerf ball, a ping pong ball, something like that, in which case this m is small. And then this spring might be a very thin, weak spring, thus making this small. And instead of moving through the air, it might be moving through pancake syrup. Right? Maybe this ping pong ball or Nerf ball with this delicate little gentle little spring is trying to move its way through pancake syrup, in which case, of course, that means that this friction term would be big. So two things happen. One is we expect a very different answer all of a sudden now that we're looking at this new physical model, and this being big, this being small. In fact, you would expect that this discriminant would be positive. And so let's study now the math side of that. What happens to the math if the discriminant is positive? Well, if the discriminant's positive, then you get two real roots. Let's go back up here. If this is positive, then that's real. And with this plus or minus, you get then two real roots. Importantly, negative real roots. Right? The real component's got to be negative. So we have two negative real roots, and we know what those solutions look like. For each root, we get an exponential. General solution then is all linear combinations of those exponentials. And what we get is solutions that are decaying. You can see they're decaying because there are these decaying exponentials. And again, importantly, don't forget that these roots are both negative, so these are indeed decaying exponentials. Decaying exponentials, yes. But there's no oscillation here. There's no sine t, cosine t here, because these solutions, these roots here, don't have any imaginary part anymore, which is the case because this discriminant is positive. So positive discriminant, no imaginary part, no oscillations. Okay. So we get a very different solution, and as well we should, because while you would imagine a cannonball attached to a spring would oscillate and slowly decay because it takes a long time for air friction to slow down a cannonball, if it was a ping pong ball attached to a weak spring, again moving through pancake syrup, well, golly, I mean, you can imagine pulling that ping pong ball just a little bit, further. Whoops. Pulling the ping pong ball a little lower, letting it go, and it's not going to go hurtling up at such a fast pace that it'll just cruise right past its natural position and keep going, only to be pushed later back down by the spring and hurtle past its natural position again. It doesn't have enough momentum to hurtle past anything, right? The overwhelmingly strong force there is going to be the resistance of the pancake syrup. And so, in fact, you expect in this case for the motion to be something like this, for it to, the spring will slowly pull it toward its natural position, but it'll just eventually maybe approach that natural position, but never actually get there. And that's physically believable. So what I think is interesting about this exploration is that even though we had an intuition, looking at these equations at the first place, we had an intuition of what we expected. We expected a decaying oscillation. The math here has actually uncovered an assumption that we were making in the way we were thinking of these problems. We were thinking of cannonballs attached to strong springs, moving through light resistance like air resistance. That was an unfair assumption. We were completely ignoring the possibility of ping pong balls moving through pancake syrup. Okay. There's one other case that we need to consider, and that is what we call the critically damped case. I'll come back to the terminology in a moment. Specifically, what if the discriminant's equal to 0? Well, if the discriminant's equal to 0, if this thing is equal to 0, then notice we only get one solution. But it's a solution with a multiplicity. One root, multiplicity is 2, so we get e to the RT and t e to the RT. And this solution here is, of course, of a slightly different form. Nevertheless, this does still approach 0, and so at a glance, these don't look terribly different. Okay. So let's talk about the terminology. Why do we call this critically damped, and why do we call this one overdamped, etc.? So the idea is, looking at this discriminant, given a mass and given a spring constant, let's talk about how much damping there is. How much friction. Damping is a term for friction in this context. So, well, there are several different cases of how much friction there might be. There might be no friction. There might be a little bit of friction, less than the critical amount. In other words, enough that keeps this still negative. Then there might be the critical amount that makes this expression exactly 0, or finally, the fourth case, there might be so much friction that that actually turns this discriminant positive. So those are the four cases, and we name them appropriately. When the discriminant's still negative, we say underdamped. There's not enough friction to make this expression positive. This case where the discriminant is positive, we call it overdamped because there's more than the necessary amount of friction to make that positive, thus overdamped. Critically damped is where, again, there is exactly the right amount of friction to make that exactly 0. And let's look and see what these roots look like in the complex plane. We've studied all these cases now. With no friction, we found that the roots were pure imaginary. When you introduce a little bit of friction, not much, still underdamped, but a little bit of friction, what happens is those roots move off of the imaginary axis and into the complex plane, like that. Still a conjugate pair, of course, complex roots. Note the real component is negative. Then with more friction, these two roots converge to a single real root, as we saw up here. Single real root. That's the critically damped case. And then as more friction is introduced, the two roots that are sort of sitting on top of each other there separate into two real roots over there. And of course this gives our overdamped case. Again, notice that these two real roots still both negative.